Jai Hind everyone. Today I am going to deliver this lecture on the topic code optimization. Earlier I have discussed different lectures in Unit 1, Unit 2, Unit 3, and now in the series of that I am going to discuss today code optimization. So everybody is aware that that is a code optimization is a phase of compiler, because compilation process is having 7 phases. It will start with the lexical analysis phase, then some particular modified program will be modified in output will be generated, and that is to be inputted to syntax analysis. After that, semantic analysis is there, then intermediate code generation is there, and that all 4 phases is the part of analysis part, because it is basically depends upon the your source code. So if you are seeing up to intermediate code generation, there will be no change in the given code, only the formats of particular code is changed, because we have to convert this code into the code which is executed by the particular machine. So in that process, code of intermediate code generations comes into the analysis part, where we have to just analyze the source code. After that, code optimization phase is there, and this code optimization phase is optional, because at every phase we are applying this optimization to improve the code, so that the overall time required for executing the code would be less. But if something is not addressed during previous phases, what we are doing, we are using this code optimization phase for improving the code. So this is the whole structure. If you will see, symbol table is working at all the level, because every time whenever we are converting the particular source code into different phases, according to different phases, then definitely some new variables is introduced, and for that purpose we have to use the symbol table, so that we have the information about the different variables which is used for this. So now you have seen source language in code optimization technique. During source language is inputted to scanner, lexical analyzer, it would generate the tokens. After that, the token is taken as input by parser, and then syntactic structure means some pasty will be generated. After that, semantic analyzer will be used, and during semantic analyzer the code optimizer is working, and after intermediate code generation the code optimizer is working. The purpose of code optimizer is to optimize the code without disturbing any particular requirement of the output of the particular code. So that is the purpose of code optimization. So after code optimization, the code will be inputted into the code generator, and then some instructions are used to execute the particular code, and after that we are getting that target code, and this target code is basically our output. If you're talking about code optimization, the first thing, because the whole compilation phases is divided into 2 passes, one is analysis pass and second one is synthesis pass. So analysis pass depends upon the source code, and synthesis part depends upon the target code. So whatever analysis and synthesis part will accumulate, these all are governed by either source code or targeted code, because this is the desired format which we require to execute. So if you're talking about the code optimization in the synthesis phase, it is a program transformation technique. Why it is program transformation technique? Because it would convert the particular format into some different format, and efforts and timing also reduce during that process, which tries to improve the intermediate code, because the input is intermediate code which is generated by intermediate code generation, that is as input for code optimization. So for code optimization we must require intermediate code, and by making it, so tries to improve the intermediate code by making it consume fewer resources, because the resources is, after all the particular things depends upon the resources. So we have to make this optimize as where we reduce less number of resources, so that if resources is less, definitely the running the speed is also boosting up, so that faster running machine code will result. So this is the purpose of code optimization. So what is the purpose of code optimization? That is which tries to improve the intermediate code. So this is the previous input, by making it consume fewer resources. So less resources are required, and so that faster running machine code will result, and the output code will be more faster than previous code. Compiler optimizing process should meet the following objective. So whenever we are applying code optimization, we must having these objectives which must meet after applying this code optimization, and these are very important objectives. So first objective is the optimization must be correct. So whatever optimization we have applying, the output, input, program fragment, all the syntax, everything will be in correct form. Nothing will change after applying this optimization. Means what would be needed after optimization, that must be correct after applying this optimization technique. It must not in any way change the meaning of the program. So whatever objective associated with the program, that must not be changed by applying this code optimization technique. That is the first part. Second one is the most important. Optimization should increase the speed and performance of the program. So if the speed and performance will not improve, your effort is not very good for improving the code. So this is very important point, because when speed is increased, performance is increased, definitely the efforts is less and we are getting the particular executive code in less time. So timing will be depend upon that. Third one is the compilation time must be kept reasonable. So whatever compilation time is required to applying this optimization, that must be reasonable. It is not much, it is not less. If less, then complexity is increased. So we have to be balanced this. And the last one is the optimization process should not delay the overall compiling process. So the time must be less. That is major criteria. If timing will be increased, then there is no advantage of applying this code optimization techniques. So whenever we are applying this code optimization, these objectives must be kept in our mind to improve the code. So these are the objectives. So the first point is what? So I am repeating the things. The purpose of code optimization is what? It consumes fewer resources. Whatever we are applying up to intermediate code, we have to improve the intermediate code. The first point. Second, the result is consume fewer resources and faster running machine code will result. So these are two targeted output required or desired by applying this code optimization, and these are the four objectives which must be met after applying this code optimization. So this is the basic function of code optimization. Now, when to optimize? Why it is needed? Firstly, we have to decide when to optimize this code. So optimization of the code is often performed at the end of the development stage, since it reduces readability and adds code that is used to increase the performance. So that is very important at the development state. The end of development state means when your particular code is generated, after that you would just try to read it or try to add something code. At that time, major process will be already performed and you have to perform less particular process for that. At that time, this code optimization is required, because only what is our objective is only to optimize the code. Rest of the part will be already arranged in the particular code. So it is very important when to optimize, because you have to focus on only the optimization process. There is nothing more is needed, nothing more is just applied at that time, because it will consume the time and it will affect the optimization process. So that is very important, the time where you want to optimize, because it is only the optimization process which improve the code, and after that you have to generate the target code. Why optimize? Because optimizing an algorithm is beyond the scope of the code optimization phase. We don't optimize the algorithm, but what we do? In the algorithm, whatever statements you have written at that particular part, we have to optimize that. So algorithm is not optimized. So the program is optimized, only the program is optimized, not algorithm, and it may involve reducing the size of the code. So optimization helps too. So why optimize? It will contain these particular 3 points. First, reduce the space consumed and increase the speed of compilation. You will see that whatever general objective we have defined, we have to categorize in these two parts, because the general objective will be converted into these two parts: when to optimize and why optimize. So why optimization is required? Because we have to reduce the particular resources and time, want to increase the time, because that is desired for our code optimization. Then manually analyzing data sets involves a lot of time. If you are analyzing whatever data sets involved manually, there is no process, because without code optimization there is no process for that. Manually we have to analyze this data set. It is really take very much time, because every data set is having different numbers, lot of lines of codes and lot of variables are there. If we are manually analyzing, it will take much time. What we do? Hence we make use of software like Tableau for data analysis. Similarly, manually performing the optimization is also tedious and is better done using a code optimizer. So for analyzing the data, we are using some different softwares, but for performing the optimization, what we are doing, we are using some code optimizer. It is kind of code which provide the facilitation of code optimization. Last, an optimized code often promotes reusability. So maybe whatever optimized code is there, we have to reuse this code, and after reusability, some particular burden will be reduced on the particular program and code segment. So this is the whole particular part, are the basics of the part of optimization: when to optimize, why to optimize, what are the basic objectives of code optimization, where it lies during whole compilation process, what is the significance of this code optimization for generating the code. So all these we have discussed in these two PPT. Now we have to going on next PPT. Important thing, what is the types of code optimization? If we're talking about, there are two types of code optimization. You have to see here, machine independent code optimization, and second one, machine dependent. If we're talking about code optimization, basically we are discussing the machine independent code optimization, because if the optimization in machine dependent, some hardware requirement is there, some hardware specification is involved in that, and that is depends upon the machine, whatever availability of machine is there. That's why here what we discuss, we are largely discuss the machine independent optimization, but still whatever optimization we are going to discuss in machine independent, that is also applied to machine dependent optimization, but subject to constraint of machine specification, that is depends upon that. So if we're talking about machine independent optimization, this code optimization phase attempts to improve the intermediate code, because whenever we are talking about optimization, then machine independent optimization will work after intermediate code generation. If you're talking about machine dependent optimization, it will work after code generation phase. So that is the basic difference, means it is up to the software part, it is up to the hardware part, because hardware is involved in that. So improve the intermediate code. Every time we are applying this code optimization after intermediate code, that will improve the intermediate code to get a better target code as the output. The objective is we are getting the better target code. That is, if this target code is very better, then there is no need for machine dependent optimization. But still, if some of the particular things is left during the code optimization phase, what we are doing, we have to apply this code optimization phase of the target code. The part of the intermediate code which is transformed here does not involve any CPU register or absolute memory location. So that is very important, because it is overall the program part. This is instruction format. This is not dependence upon the hardware, but still whatever hardware availability is there, whenever you are running a program, that must be desired, but that not directly affect, because it is the part of the program, because it will just optimize the source code, not the combination generated by the target code. So this is called machine independent optimization. So machine independent optimization is the real phase of code optimization in whole compilation process. If you are talking about machine dependent optimization, so machine dependent optimization done after the target code has been generated and when the code is transformed according to the target machine architecture. So it is after code generation phase. That's why it is called machine dependent optimization, because when target code is generated, after target code generated, whatever things are left in terms of optimization, we are applying this. So mostly the process is involved in both of the cases is the same, but some of the additional optimization is required for machine dependent optimization, like peephole optimization. That is additional optimization which is required for the machine dependent optimization. Peephole optimization is not used for machine independent optimization, but constant folding and local optimization and function transferring, preserving transformations, these all are used for machine dependent optimizations also. It involves CPU registers because hardware is involved and may have absolute memory references rather than relative references. So machine dependent optimizers put efforts to take maximum advantage of the memory hierarchy. So some hardware part is also involved during machine dependent optimization. And if you are saying in the compiler, that is not the largely part. The largely part of the optimization is machine independent optimization. Now we are going to discuss this machine independent optimization. Where to apply optimization? There are three particular parts where we can apply the optimization. Initially the source program, because when program is there, some of the optimization will be applied in every phases, but that is very reasonable, very small, and that does not affect the overall program structure because it is very small. Then intermediate code, it would optimize the whole program and optimizing a better target for a better target code. And after target code, it is done by the compiler because hardware is involved, some particular software, hardware, both combination is involved, the target code may be generated. After that, some optimization is required. So these are three particular places where we can apply this optimization. Okay. So if you are talking about source program, if you are going to detail, optimizing the source program involves making changes to the algorithm or changing the loop structure. User is the actor here. So here user is the actor here because source program is inputted into that. Intermediate code, optimizing the intermediate code involves changing the address calculations and transforming the procedure calls involved. Here compiler is the actor because it is the process of compilation, and compiler is as the actor because it is a program which use this process of optimization to optimize the intermediate code for producing a better target code. And then target code, optimizing the target code is done by the compiler. Uses of registers, select and move instruction is part of the optimization involved in the target code. So in target code, some instruction, registers, hardware part is also involved. So machine is there, but the whole process will be governed by the compiler. So these are three places where we apply optimization, but we are discussing this part as more because it is the part of compilation process. Now, what are the principal sources of optimization? If you are talking about principal sources of optimization, so there are two ways of optimization. One is global optimization. Second one is local optimization. So if you are talking about global optimization, the transformation are applied to large program segments that includes functions, procedures and loops. So global optimizations means some chunk of code is there, some specific area is there, like function. If you are talking about a function is a particular part of the program which is a separate part where we can execute a piece of code and that is taken as by parameter and some output is produces and that is again used in the program. So these kind of larger structures comes into the category of global optimizations. If you're talking about local optimization, that is basically in between global optimization. Whatever optimization you are putting into that means if a loop is there and in between loop all the optimization if you are applying in the loop statements, that is called basically local optimization because the loop is a local area. Loop for the overall program it is a global area, but into the loop that is local area. So this is the principal sources, global, local optimizations. If you're talking about global optimization, then different kinds of optimization is there. Like if you are local optimization, if you are talking about, like if you are putting this AI equals to AI plus 1. Suppose this statement is written. So this statement is not up to the optimized form because it will take more time. Whenever you require to execute this particular part, every time the I plus 1 is initially calculated, then that mapping is with capital A is there, and then again it will start it. So if you convert this into that, this is called simple optimization. If you are converting it into AI equals to AB and B equals to I plus 1, so it would be easy. It would be easy to mapping, and it will take less time, and the clear results will be displayed. So we have to convert. This is called simple optimization. Then loop optimization, because loop optimization is a major part where 90-10 rule is applied. 90-10 rule is applied because 90% efforts will be putted for 10% loop part of the program, because if any unwanted thing that is not part of the loop is the part of loop, and when you are executed, because loop is having 1000, 2000 number of iterations, if one statement is additionally added into that which is not depends upon the index of the loop, then it will be a major mistake, because that particular statement is running out of different iteration which is involved in the loop. So loop is very sensitive part, and we are going to discuss the loop transformation is in very important manner. In this lecture I am only giving the basics, what types of basic optimizations are involved, but loop optimization is a basic topic where we need to execute that. So loop optimization is very important. Third is algorithm optimization. We have already discussed in algorithm optimization. If you are selecting the different algorithms for executing a particular program, definitely the algorithms also impact different. If you are talking about sorting algorithm, so if 25 number of elements is there, then only insertion sort is giving the best performance rather than your heap sort and second one is quick sort if you are applying any. But if you logically see that the complexity of heap sort and quick sort is much better than insertion sort, but still that depends, it depends upon the input side. So if the more input size is there, you can apply this heap sort or merge sort for sorting. So algorithm selection is also important part, but that is not the part of this code optimization, but I am talking about a general optimization. Third is the user implementation detail is hidden. Means the implementation details is hidden for user, so that user is only executed that much part where the code will not affected. Okay, so that is also an important kind of optimization, so that our code is designed in different abstractions are there over there, through which user can only the concern about their executing area, not he is involved into the code which is written by the particular user developer, because developer's point of view is different and user point of view difference. So these are kind of optimization sources, and we have to apply these optimization into these sources. Here we are only discussing the semantic preserving transformation. This is kind of local optimization we can call it. Why? Because simple optimization which is involved in global optimization will be used over here. So there are number of ways in which a compiler can improve a program without changing the function it computes. So that is very important. We cannot change the function, because whatever output we desired, that must become after applying this optimization. So we must see this. Then these are different kind of optimizations. One is common sub-expression elimination, copy propagation, dead code elimination, constant folding. These are function preserving or semantic preserving transformation. We shall consider each in turn. Okay, so if we're talking about these transformations, these are called semantic preserving transformations, because semantic preserving transformations are basically related to semantics, and it is a kind of local optimizations. Common sub-expression elimination is also done with DAG. We are using directed acyclic graph in which triples are used, and we can convert the particular sequence into triples and then derive a DAG. And in DAG, if you are getting more than one variable for one particular statement, definitely it will be coming into the common sub-expression elimination. So these are different functions or different function preserving transformations which we are going to discuss in next particular PPTs. So there are number of ways in which a compiler can improve a program without changing the function it computes. These are particular function preserving transformations. Now copy propagation, what does it means? Copy propagation is what if suppose some particular statement are in the form of x equals to a plus t, y equals to a plus t, z equals to a plus t. Some copied elements are there and these three variables are there which is defined by that. So if we are going to execute these particular variables x equals to a plus t, every time a plus t is executed and then the value is transformed to x. Similarly again a plus t is executed, the value is transformed to y, and a plus t is executed and then value is transformed to z. It would put a lot of efforts to execute these kind of a statement. So what we are doing, we are applying copy propagation and we are just here writing c equals to a plus t, then x equals to c, y equals to c, and z equals to c. So this is very easy for execution and it will put a small effort for executing this statement. So that is called basically copy propagation. So given an assignment x equals to y, replace later uses of x with uses of y provided there are no intervening assignment to x or y. When it is performed at any level but usually early in the optimization process, what is the result? This is smaller code. So you have to see the difference in that. So it is a smaller code and it is a larger code. So here f equals to g, for example xi equals to f equals to z are called copy statement or copies. Use of g for f whenever possible after copy statement. For example xi equals to a, sum equals to xi plus a. So xi plus a, sum equals to a plus a. So whatever xi equals to a is there, so you can replace this xi into a. So it is very easy rather than xi, because xi is a basically one dimensional array. If you are going to convert the particular xi, want to execute this xi, definitely firstly you have to finding out the base address of array, then their index, then mapping it, then finding out the location, that location value is taken, and then after that you have to add this value is that. So it is very largest particular code as compared to this. So if you are putting that variable is directly because this variable is stored into that, so we can convert it into the form of copy propagation. Now dead code elimination. So dead code elimination is what the part, whatever code that is not the part of whole program and it will not contributed in anywhere, that is called basically dead code. So dead code are the portions of the program which will not executed in any path of the program, can be removed. We can find two ways to finding out this dead code. One is DAG and second one is directly you can use a particular code and you can find manually into that dead code. In DAG, if you are designing a DAG for any triples or quadruples or any particular program fragment, if some of the portion is not connected with the overall DAG of the program and it is separated from that, definitely it is the part of dead code because it does not contribute into the execution of the whole program. So no control flows into a basic blocks. These are examples. A variable is dead at a point, its value is not used anywhere in the program. An assignment is dead, assigns a value to a dead variable. So dead variable, which is dead variable if you are talking about that? So x equals to y minus 5. Because there is no use of any value, x value is anywhere, that's why it is dead. If in a simple example, suppose we are putting debug equals to 0, okay, and we are writing if debug then x equals to y, suppose this code is there. So if you are seeing that, because we have already giving the value of debug equals to 0, so whenever if debug means it cannot true for any particular execution, so that's why this is your dead code. So such kind of codes are dead code and it will be a burden for the program. So we have to identify such kind of dead code during the optimization and eliminate these dead codes from the program. So this example I have already said that this example already debug equals to 0, if debug print can be eliminated because it is not required. Now compile time evaluation. So if you are talking about compile time evaluation, there are two ways. One is constant folding and next one is constant propagation. So if you are talking about constant folding, so constant folding is very basic thing because sometime we are putting the numerical variables into this type. Suppose a equals to x plus 7 and x equals to 5. So if you are seeing this, because x is having value already 5, so a equals to x plus 7. Firstly, we have to generate this statement, this, then the x value is associated with that, then directly we are getting that. So if you are converting it, x equals to 5 and a equals to 12. So it is called basically constant folding. And constant propagation is also a technique like constant, like copy propagation, because we have to propagate the value of constant. So we will see that if you are talking about constant propagation, replace a variable with constant which has been assigned to the earlier, like pi equals to 3.142.6, area equals to pi into r square. So we have to directly put is that, means we have to put this pi value directly here, so that that assignment firstly execute the pi, then check the value stored in the place of pi, then this value is called by the program, then this value is placed over here. So this will take a lot of time. So what we are doing, if that value is there, so this is the basically constant propagation. Okay, in next lectures we will cover the next topic. Thank you very much.